Welcome back. We have one more section to cover here in Chapter 3. This lesson is on the linear correlation coefficient. Here are three scatter plots. As you look from left to right, you will see that the degree of correlation is increasing. We go from a moderate to strong linear correlation on the left to a pretty strong correlation in the middle to almost a straight line on the right. The problem that we have, though, is we have no measure yet of how strongly a data set is, how strongly the x's and the y's are correlated. We've only talked about it in terms of weak and moderate and strong and perfect. And that's compounded by the fact that all three of these scatter plots have the same line of best fit. Those red lines are the same slope. They have the same slope. They have the same y-intercept. The line isn't telling us anything about how well the line models the data. So we need a new measure. And that measure is referred to as the correlation coefficient. The correlation coefficient is expressed as lowercase r. It is a unitless measure that describes the strength of the linear association between two variables, and it doesn't matter which one is listed first. And that means that if for some reason we had swapped the independent and dependent variables, if we had swapped the values of x and y across the board, we would still get the same value for r. And there is a full name listed here for those of you who like to know more about the statistics that we study. The linear correlation coefficient has the official name, the Pearson product moment correlation coefficient. For our purposes, we're just going to call it the correlation coefficient, or simply R. No matter what we do, R can never be larger than +1. It can never be smaller than -1. The closer we get to those extremes, the more linear the data points are. At 0, there is no linear correlation whatsoever. So you can imagine, try to find a way to draw a line that comes anywhere close to hitting as many of these points, or getting close to as many of these points as possible. You can't do it. There is no discernible relationship here between x and y. Certainly not a linear one. Out at the extremes, if r is +1, or if r is -1, we are saying that there is a perfect linear correlation between x and y, that every data point lies on the least squares line. When r is +1, we have a positive slope. X increases means y increases. When r is -1, our best fit line has a negative slope. As x increases, y is decreasing. So that means that anywhere between 0 and 1, we have a positive correlation. As x goes up, y goes up with it, as long as r is positive. Meanwhile, when r is negative, it is a negative correlation. As x increases, y is decreasing. So how do we find r? Well, it's a formula based on 3 other formulas. Now, 2 of them you are familiar with. We have already in our travels looked at SSXY and SSX. SSY is a new one. It is structured in pretty much the same way that we were using for SSXY and SSX. For the SSY formula, it is the summation of the y squareds. That means we need a new column in our table. Our 4-column table that we used last section is now going to be a 5-column table. We'll need a column for the y squared. So we'll add up the y squared for each ordered pair, and that'll give us the summation of the y squareds. We'll add up the y's and square it, same as what we were doing before, where we were adding up the x's and squaring, or we were adding up the x's, adding up the y's, and multiplying. In this case, we are adding the y's and squaring it, and as always, dividing by n. So it's three flavors of the same formula that come together to form r, where r is SSXY in the numerator, and the denominator is the square root of the product of SSX and SSY. So here's our example. How much of a correlation is there between IQ and GPA? And you're probably thinking, yeah, those smart kids, they have good grades, but not necessarily. We have a student on the table with an IQ measured at 121, and their grade point average is a solid 3.8. But we also have an above average student, 115 for GPA, or for IQ rather. That's one standard deviation above the mean. They're barely doing better than a C average. And on the other extreme, we have some low IQ students with low GPAs. The 76 has a GPA of 1.8. But we've also got some success stories here. We've got somebody who is just below average IQ, 98, and their GPA is 3.5. So maybe there is a solid correlation, maybe there isn't. But either way, let's try to measure what the correlation is. First off, though, a scatter plot for your consideration. Would you say that on the whole, that IQ and GPA are positively or negatively correlated? Yeah, that's right. You would say that there's a positive correlation. It appears that on the whole, as IQ increases, GPA is going up with it. So here's that same kind of table that we created last section, where we had a column for x and a column for y, and we needed the x squareds, we needed the xy's. We've now included a new column for the y squareds. So we need to fill in one additional column and get a summation there. That's not a big deal. As we do that, as we work our way through this, an x value of 117 corresponds with x squared being 13,689, with y being 3.7. When we square that, we'll get y squared being 13.7. I realize that's not perfect. You're getting a two-digit decimal answer here, and that's fine. And then the product of x and y, 117 times 3.7 is 432.9. And we would repeat that for each of these lines. 92 squared is 8,464, 102 squared is 10,404, and so on, to get us all the way down to a sum for the x squareds, which I'll show you in a moment. Same thing would happen with the y squareds. 2.6 squared is 6.8, and so on. And we'll finish the job with 92 times 2.6 being 239.2, and so on. We need column totals. The sum of all of the x values is 1,227. The sum of the y's is 36.13. The x squareds add to 127,535. The y squareds add to 114.9, and the xy's add to 3,780.3. Another piece of useful information for us would be the sum of the x's squared. 1,227 squared is 1,505,529, and the square of 36.3 for the sum of the y's quantity squared is 1,317.7. From here, we have all the numbers that we need. We'll get SSXY for the numerator in the R formula. We'll take the sum of the xy's, that 3780.3, and subtract from it 1227 times 36.3, all divided by 12. And that gives us a value for SSXY of 68.63. The fact that SSXY is positive is our sign that R will be positive. If SSXY were negative, that would assure us that R would be negative. We bring in the two parts of the denominator for SSXY. It's 127,535 minus 1227 squared over 12. And that 1227 squared, by the way, that was the 1.5 million-ish number that we had before, for a value of SSX of 2074.25. For SSY, we take the sum of the y squareds, 114.9, and we subtract from it the sum of the y's squared. That was the 1,317.7 that I had shown you on the previous slide, divided by 12 again, gives us a value for SSY of 5.09. And from here we can make the big finish. We drop the three numbers into the formula for R. 68.63 over the square root of 2074.25 times 5.09 gives us an R value of about 0.67. That would, in most people's minds, be a moderate, borderline strong correlation between X and Y. But it isn't perfect. And so we introduced what's called the coefficient of determination, and that's R squared. This is a measure of how much influence X has on Y. So for example, in the IQ versus GPA problem that we just did, we said that R was 0.67. It was 0.6679. If we square that number, we'll get about 0.45. And the meaning of this is pretty straightforward, actually. What we're able to say here is 45%, there's your 0.45, 45% of the variation in GPA can be attributed to the variation in X, according to our results. What that means is the other 55% is due to something else. Maybe it's random chance, maybe it's the presence of other variables, and there's a lot of reasons why a student with a high IQ would not necessarily have a high GPA, or why a student with a low IQ would not necessarily have a low GPA. There's your 55% right there. It's your turn. In one of the Boston city parks, there has been a problem with muggings in the summer months. A police cadet took a random sample of 10 days out of the 90-day summer and compiled the following data. For each day, X represents the number of police officers on duty in the park, and Y represents the number of reported muggings on that day. We are asked, how much of a correlation is there between the number of on-duty officers and the number of muggings? If your gut instinct was more police officers on patrol would lead to less muggings, the scatter plot seems to bear that out. On the days when there were many more patrolmen than on other days, there were few muggings. And when there weren't a whole lot of patrolmen out and about, there was a relatively high number of muggings. We have a negative correlation here, and it seems to be, from the scatter plot, it appears that this is a pretty high negative correlation. So you generate the table with the x's and the y's. The x squareds add to 1,347, the y squareds added to 295, and the xy's added to 343. The x's were a total of 103 police officer shifts, the y's a total of 47 muggings over the 10 days that were sampled. plug everything in. SSX was 286.1, and then we needed SSY for the denominator. That was 74.1. That's where we're getting for the denominator in the R formula the square root of 286.1 times 74.1. Meanwhile, for the numerator, SSXY evaluated at negative 141.1. There's your denominator in the R formula, and putting everything together, do the calculation here, and you will find that R is approximately negative 0.97. This is a very, very strong negative correlation, and a convincingly strong negative correlation that increasing the number of patrolmen or patrolwomen to, hey, it's the 21st century, as we increase the number of police officers that are on duty in the park, the number of muggings went down. That's all for today. Thank you for watching, guys. See you next time.